Hi, my name is Joel Rorseth. I'm a master's student in computer science at the University of Waterloo. Today I'll be presenting the paper Device Placement Optimization with Reinforcement Learning by Mirhoseini et al. Let's get to it. First, a quick roadmap. We'll begin by introducing the device placement optimization problem and explaining any necessary background information. Then we'll get into the reinforcement learning-based solution that the authors propose in this paper. Then we'll discuss the evaluation that takes place in the paper, and follow this up with a conclusion summarizing some of the main points and possible future directions of research. Up first, an introduction to the problem at a high level, and some background information for context. Before going any further, let's discuss distributed deep neural network training. The success of deep neural networks has come at the cost of increased size and computational requirements for both training and inference. Now, existing parallelization strategies for training a deep neural network fall into two predominant categories, being model parallelism and data parallelism. Data parallelism essentially replicates the model to n workers and then distributes the data proportionally to each of these workers. In model parallelism, the deep neural network operators, or usually layers, are partitioned across these n workers, and then they operate sequentially to train all the data. Now that we're familiar with different types of parallel deep neural network training, let's focus on one in particular, that being model parallelism. Now, model parallelism requires some sort of partitioning of the deep neural network operators to devices within a heterogeneous distributed environment. And by devices we mean CPUs or GPUs. And a heterogeneous distributed environment is just a collection of machines that have any number of CPUs and GPUs. Now, typically, practitioners will specify these device placements manually, using simple heuristics or intuition. But ideally, we should have an algorithm that will mathematically determine a device placement that is optimal. And by optimal, we mean reduce the execution time of the training process and inference. Now, with this, we would like to eliminate the need for experts and even improve upon their suggested placements, because as we will see in the evaluation section, sometimes the recommended placements are not optimal. As the size of deep neural networks grow and the distributed environments in which we train them also grow, then so too will the placement space. Now, this placement space can be enormous, and reinforcement learning is very well suited for navigating this placement space. We want to navigate it and avoid wasting time on suboptimal placements and hopefully converge quickly upon more optimal placements. Now, this paper explores this idea, and you can see that presented on the right, we have the high-level solution for reinforcement learning. Now, it is essentially broken down into the policy, which yields placements, and these placements are evaluated in the environment, meaning that they are trained, these models with their placement are trained, and then we measure the execution time of training and inference, and formulate this into a reward or cost function, and then using a neural network representation for the policy, we can calculate policy gradients with respect to this execution time and then update the model so that we basically predict better placements in subsequent iterations. Now, before we get into more detail of the proposed model, let's discuss some related works. Reinforcement learning has been applied to similar problems in the past, such as job scheduling and resource management, or combinatorial optimization in several works. But as far as I can tell, the proposed model is the first to apply reinforcement learning to device placement optimization. What sets this apart from other research in this field and for this problem is its focus on practical large-scale models and data, and the formulation of an objective function that will minimize placement runtime. Now, graph partitioning can also be applied to device optimization, and the authors do this in the paper. They actually employ the Scotch optimizer from Pellegrini, and we'll use this as a baseline in the evaluation section. Okay, let's dive into the details of the proposed model. First, let's define this problem mathematically. In this paper, the authors are from Google Research, so we will be using TensorFlow to model our problem. Now, a TensorFlow computation graph, G, consists of two things: a list of M operations and a list of D available devices. So now, a placement P is the assignment of operations to devices, such that the placement has M elements, one for each operation, and each element is one of the available devices. Now, R of P denotes the execution time for G under the placement P. And particularly in this paper, the authors propose, for increased robustness, that we actually use the square root of R of P and denote that as capital R of P. So that's what we'll use moving forward. Now, to state the problem mathematically, and for the purposes of reinforcement learning, find the optimal device placement P that minimizes R of P. Now let's formulate the problem using reinforcement learning. We want to train a stochastic policy, so let's call that pi of P given G and theta. We also want to minimize the objective function, so let's define one. Our objective function will be J of theta, which is equal to the expectation over placements drawn from the stochastic policy of the execution time R of P given G. The authors propose the use of atom optimizer along with policy gradients from reinforce. So let's define a gradient function of our objective function. So the gradient with respect to theta of our objective function, J of theta, is equal to the expectation of over all placements drawn from the stochastic policy of the execution time, RP, multiplied by the gradient with respect to theta of the log probability of P given G and theta. Now in practice, we need to estimate this. We're going to do so by drawing K samples. So let's redefine this so that we can calculate it using samples. So equivalently, the gradient of the objective function is defined as the average over K samples of the execution time of the sample minus a baseline B multiplied by the gradient with respect to theta of the log probability of that sample, Pi, given G and theta. Now the baseline, B, is meant to reduce variance. The author suggests that a moving average works well, so that's what we'll go with for the duration of the paper. As you may have guessed in the previous explanation, our policy needs to be represented by some sort of neural network in order to justify the use of theta in our policy gradient step. So the policy is defined using a sequence-to-sequence deep neural network model, and in particular, we're going to use LSTM and an attention mechanism. And again, this paper, we are yielding placements in the policy. So this model essentially incorporates two parts: the encoder and the decoder. The encoder simply embeds a sequence of operations in G. The embeddings consist of the operation type, which might be a matmul or a conv2d operation, the output shape, and some input-output adjacency info. The decoder, however, outputs device assignments for each of the operations in the graph. The outputs have tunable embeddings, and they are fed to the subsequent decoder time steps. Here we have a nice diagram to illustrate the architecture of the policy network and sequence-to-sequence model. You can see the embeddings that embed the three types of information in the encoder, which is sort of the left half of this diagram here. And then on the right half, we have the decoder. And you can see the outputs from each decoder time step are being fed to subsequent time steps. To train the policy model itself, the authors use asynchronous distributed training, which is illustrated in the diagram on the right. In this strategy, they create controllers to execute the policy. Each controller samples K placements, where K is the number of samples that we previously established for the gradient calculation. Each of these K placements is then assigned to one of the controller's K workers. Each of the workers reports the execution time from executing the placement, back to the controller, and the controller then calculates gradients and sends them to the parameter server for updating the model. Now, there is an inherent trade-off between the number of workers, where more workers increases the accuracy of the policy gradient estimates, but at the cost of resource utilization, meaning more idle workers. Before moving on to the evaluation section, I'd like to point out a couple of implementation details that are noted by the authors. The authors choose to use 20 controllers, each with 4 or 8 workers depending on the experiment at hand. They found that finding optimal placements took anywhere from 12 to 27 hours in this configuration. But using different configurations would likely lead to different timeframes. Each controller maintains a separate baseline B. This is for the purpose of increasing stability, which is negatively affected by discrepancies between the heterogeneous machines. To scale better, operations are manually co-located on the same device. TensorFlow has a default method of doing this, and so default co-location groups are used. Additionally, the authors propose a heuristic wherein they co-locate operations whose output is sent to only one other operation in the graph. Lastly, co-location groups are manually specified by the authors differently for each type of model that will be tested in the experiment. This is done as a pre-processing step. Let's review some of the experiments carried out in the paper and dive deeper into the performance of the proposed model. In their experiments, the authors compare the placements derived for 3 deep learning models. First being recurrent neural network language model with LSTM layers, abbreviated as RNN-LM. Next is neural machine translation with attention, NMT. The final is Inception v3. To compare the placements, we will essentially compare them on the basis of their training execution time, which we'll calculate as the time for 1 forward pass plus 1 backward pass and 1 parameter update. Although there were no other reinforcement learning-based methods to derive placements at the time the paper was published, the authors have managed to establish a collection of other baseline methods. So the first is single CPU, which is just executing a neural network only on 1 CPU. There's single GPU, executing the neural network on 1 GPU, or the CPU if no GPU is available. There's Scotch, which is the graph partitioning algorithm that we discussed earlier from Pellegrini. There's MinCut, which is exactly the same as Scotch, but we use GPUs only when possible. And lastly, expert design, which we use model-specific placements suggested as optimal in the literature. In this table, pulled from the paper, the authors, they describe the relative improvement of RL-based method over all the other methods in terms of execution cost. On the furthest right column, we see a percentage value that quantifies the speed up of the RL-based method over the best non-RL-based method. In the top row, for RNN-LM with batch size 64, we see that the best other method is single GPU with execution time of 1.57. Now, for both configurations of 2 GPUs and 4 GPUs, we see that the RL-based method essentially recovered the fact that a single GPU configuration is ideal here. In the second row, NMT with batch size 64, we see that the RL-based method improved upon the optimal expert methods by a factor of 20.6% for 4 GPUs and 23.5% with 2 GPUs. Now, these speedups, they are due to the fact that the RL-based method learned to put the embedding lookup on the CPU. Now, in the last row, for Inception v3 with batch size 32, again, other than the RL-based method, the ideal is to use single GPU with an execution time of 4.60 for both 2 and 4 GPUs. Now, in the case of 2 GPUs, the RL-based method discovers that it is actually optimal to put the entire model on one GPU instead of using both. But when we have 4 GPUs, then it actually makes sense to distribute it across 4 GPUs, and in which case, we observe a 19% improvement. In this figure, the authors have visualized an example placement produced by the RL-based method for the neural machine translation model. The top 3 rows are layers in the encoder, and the bottom rows are layers in the decoder. Different devices are denoted by different colors, where white actually denotes a CPU device, and all the other colors denote GPU devices. Like previously mentioned, we can see that this particular example placement has learned that embedding layers should, in an optimal configuration, be assigned to the CPU since they are not as computationally intensive. Using the neural machine translation model once again as an example, this chart illustrates 2 things. We see that the RL-based placement has improved training perplexity when compared to the human expert. Also, we see that the reinforcement learning-based placement runs faster than the expert design placement. You see the red curve gives about 165 hours of training time for the RL-based placement, where the human expert, that solution takes about 229 hours to train. So this graph really does a good job at illustrating the total speed up of training time. In this case, it's 27.8%. In these diagrams, the authors are profiling the placements found for the Inception v3 model using our RL-based approach and a synchronous towers approach, which is parallel execution with synchronous weight updates. So the synchronous towers approach distributes the workload evenly, as you can see in the left diagram, but the RL-based method finds a very unbalanced placement as being optimal. And believe it or not, this actually is an improvement. The RL-based method was able to learn that many dependencies exist within the Inception v3 model, and truly, model parallelism should be proportionally reduced, and it is very clearly doing so. As you can see, GPU 3 is very minimally utilized here. On the right, we can see that operations on each GPU in the synchronous towers approach is much higher on average than the RL-based placement, and this is because they are receiving data from the CPU, but the memory activities in the RL-based placement are actually between GPUs only, so this does save a lot on the memory overhead. Let's wrap up our discussion with a few points about what the main contributions were and possibilities for future work. This paper is certainly a novel and significant contribution to distributed deep neural network training and device placement research. Now, there are several important advantages that have been brought with this model, one of which is that it has essentially been able to learn to balance the trade-off between parallelism and inter-device communication. Now, this is a trade-off. You can't really get both, but you can find a balance between the two depending on the data set at hand and the model at hand. Now, you can also learn non-trivial optimal device placements. These are just not going to be likely proposed by humans, and reinforcement learning is the perfect algorithm to explore and discover these without wasting time on suboptimal solutions. It can also find optimal placements that minimize the training and inference execution time within a distributed environment, of course. Now, the formalization of device placement optimization as a reinforcement learning problem is also novel and is interesting in the context of reinforcement learning. The objective function, with its matching sample-based gradient update, is very much novel, and the sequence-to-sequence model for flexible policy representation is very much useful and novel as well. The empirical evaluation that is presented really does illustrate the optimality of the discovered placements and proves the worth of the proposed model. For future work, I've noted some potential improvements to the paper itself, along with possible extensions of the model that could be explored in future research. To start, I think it would be great to extend the existing model to not only balance model parallelism, but also data parallelism. I think the paper was a little bit unclear on whether it supported or handled data parallelism. Clearly, the focus was on model parallelism, where we mapped operations onto devices. It would be great to explore newer hybrid parallelism approaches, such as pipeline parallelism. In addition, it would be great to generalize the model to work with other machine learning frameworks, since this particular model was implemented in TensorFlow. I think the problem was formulated generically enough that it could easily be adapted to other frameworks, and it would be great to see this done in an experiment. Concerning the paper, an improved explanation for the policy network would be great. In particular, I would have liked more discussion on the effect, the capabilities, the motivations behind using the LSTM and the attention mechanism in the sequence-to-sequence model that we used for the policy. I also would have liked to see more mathematical discussion of the reinforcement learning portion of the model, and I think a comparison with other deep reinforcement learning models would have put this in context a little bit better. I've listed a few references here, the first one being the paper itself, and the second one being a survey on distributed, parallelized deep neural network training that it was used to create this presentation. That concludes my presentation for today. Thank you for listening, and feel free to contact me with any questions or comments. You can reach me at joel.rorseth@uwaterloo.ca. Thanks.